This is part two of a two-part series that looks at the science behind the fact that houses do so well so long as they are bolted to the foundation. Now, as introduction, I'd like to review some of what we saw in part one. Behind me you see a photograph that you've probably seen in some other places in this video series. And the reason I like to show this to people is because it shows exactly what a retrofit is supposed to do and why it is so important. So this house is more or less intact, except it fell from its foundation, which is a big deal, which means it's not intact. And if you just look at it structurally, it's all there. The walls are there, the roof is there, the windows aren't broken. You know, it's really an amazing photograph, which is why I show it so often. Now, there are reasons for that, and the reasons are the strength of the existing materials that old houses are made out of, which is considerable, and then the fact that it has cross walls. And we're going to look at both those things right now. Now, a very, very interesting thing is there were tests that were done on existing building materials after the 1971 San Fernando earthquake, and that became a table in the California existing building code. So we're going to be looking at that table and how to use it, how that table has evolved over time, and we're going to also hear about a first witness account of how that table was made. Now, there are two reasons why that house did so well in that earthquake. And the first one is because houses are cubes. A cube is a very, very strong geometric shape, kind of like a shoebox. So just imagine a house. The roof is the top of the cube, the walls are the sides of the cube, and the floor is the base of the cube. So we have a very, very, just a great big cube is what it is. Now, inside that cube, you have lots of smaller cubes. So you have bedrooms, you have bathrooms, you have kitchens, you have hallways, you have all sorts of things that are also cubic, cubic shapes. So you have all those smaller cubes within a larger cube. And so in the end, you end up with a shape that's, it's just geometrically very, very strong. If you were to take a shoebox and you throw it on the floor, I mean, not much is going to happen to it. And the same, has to do with houses as far as they're being geometrically strong. I mentioned earlier that we would be looking at a table in the California existing building code that addresses the earthquake resistance of old building materials. So, for example, plaster walls. No one makes a house with plaster walls anymore. They're made out of sheetrock. But we do need to know how much earthquake force they can resist when we're designing a retrofit. Now, when we talk about these materials, we rate them in pounds of resistance they have against an earthquake. So anyway, for example, we'll say that 5,000 pounds of force is going to be pushing against the house, and then we'll say there's 5,000 pounds of resistance offered by a building material. Now, it needs to be made clear that forces do not push against houses. That's not what happens. What happens is there's a ground acceleration underneath the house, and the way the house responds is exactly as if something would be pushing against the house. So for conceptual reasons, and because it's much easier to understand, I'll be talking about pounds of force as if they're pushing against the house. So keep that in mind from here on. So what we have here is the ground acceleration is pushing at the base of the house, just like this. So what's happening is the ground is moving this way, and inertia is causing this house to lean, and it's going to want to try to slide off the foundation right here. So in a seismic retrofit, we're trying to prevent that from happening. So I want you to notice how this movement right here, underneath the house, is identical, at least what happens here, is identical to a force that is pushing on the house right here. So what we do is we figure out the weight of the house, and we have the ground acceleration underneath the house. And when we multiply those two together, we end up with pounds of force. So we look at, we translate that ground acceleration into pounds of force that are pushing against the house. So all the hardware and plywood and whatever it is that we happen to use in a seismic retrofit is designed to resist a certain number of pounds of force. The other thing has to do with cross walls. Now, cross walls are the interior of your house. So, for example, just look down, usually down the middle of your house, you'll have a great big wall. The bedrooms will have walls. The bathrooms, the kitchens, there'll be walls everywhere, partition walls inside the house, and each one of those can also resist earthquake force. So just imagine, here's earthquake force coming in this direction, and then this wall, this wall, this wall, and this wall will all resist that earthquake force. And on top of that, the exterior walls will also resist that force. So that's a whole lot of wall to resist that kind of force and to keep the house intact. Now the same thing, when earthquake forces come in this direction, these interior walls here and here, and also on the outsides here and here, they will also resist that kind of force. So, that's why these houses do so well, is because they just have so much internal strength due to the geometric shape of the cube and also due to the earthquake resisting abilities of the cross walls inside the house. So when people try to tell you, hey, you need to take the siding off and put in some plywood, or hey, we need to, take your roof apart and put in some metal, or hey, let's take the sheetrock out of the inside and put in some plywood and a shear wall. That's just all a bunch of nonsense. That's not what happens to actual houses, and this is the reason. And in a minute, we're actually going to go into the tests that were done and certain sections of the building code which confirm what I'm telling you right now. I mentioned previously that we would be looking at a part of the California existing building code that address existing building materials. So that, like the old stuff, they'd be like plaster walls, they don't make those anymore, floors that are made out of boards of wood, that sort of thing. They were, no one knows how much earthquake force those can resist because there's no reports that came with them. For example, for new building materials like plywood or bolts or anything, there's a test report, they've been all kinds of tests, government supervision, etc. You know exactly what you're getting into. But with existing building materials, there's no way to know. It's just all you can do is take it apart, see how it was built, and then rebuild it and test it. And that's what we're going to be looking at right now. After a big earthquake in 1971 in San Fernando, the Structural Engineers Association of Southern California, they got together and went to evaluate the damage. And what they discovered was that they couldn't tell what happened to the brick buildings because they all turned into a big pile of rubble. And so what happened was they said, we can't figure out a way to retrofit these things if we don't know how they're built. And so what they did is they applied to the National Science Foundation, and they were given a grant to study brick buildings and do testing and evaluations of the materials that they were made out of. So they actually literally traveled all over the country, and they also did a series of tests of existing building materials. And so that's what cross walls are made out of, and that's also what cripple walls are made out of. So they did all these tests. Now, they were able to use a laboratory with Rockwell International Aerospace. And Rockwell International Aerospace, they had an absolutely amazing test setup. Airplane lands, or when a rocket takes off, or when it when it's subjected to lots of wind, and they had all these things in their laboratory with which they could test building materials. They took the actual data from the earthquake, they put it into this test equipment, and then the test equipment would create a test which would mimic exactly what an earthquake looked like. And then they came up with this table right here. So this table, you'll see the cross walls are part of this table, and then all the earthquake resistance that these cross walls have are rated. So let's go ahead and see how we would use this table in the analysis of the earthquake resistance of an actual house. So let's assume we have a house that's built before 1940, it's stucco, and the walls are made out of plaster. And we would look at this table, and it says here, we're looking at cross walls, plaster on wood or metal lath. Now lath is the backing. So plaster on the inside of the house, that'll always be covered, have wood lath. Now, if you go into the stucco, you will see either wood lath, or you will see wood lath in these big boards, or you'll see chicken wire. So that's the metal lath. So we're going to find one of those two things. And then also sometimes on the interior, we find something called gypsum lath. And that's usually like a sheetrock stuff. We call it button boards. It's got holes in it. So for example, for plaster on wood or metal lath, it can resist 600 pounds per linear foot. And so what we do is we'll, look at a house and we'll take a look at a wall. And let's say the wall is 10 feet long. And we'll say, okay, one side can resist 600 pounds per linear foot. Other side can resist 600 pounds per linear foot. And total, the whole wall can resist 12,000 pounds of earthquake force. Now let's say we're doing the same thing on looking at the stucco cripple wall, because the cripple wall is the weak spot. And so we look at the cripple wall and we say, okay, this cripple wall, according to this table, can resist 600 pounds per linear foot. And so we, take the length of the cripple wall. Let's say it's, 20 feet long. We multiply that times 600, and we end up, again, 12,000 pounds of resistance on that cripple wall. So that is how this table used in the analysis of an existing building. Now, the reason I happen to have all this background is the only living witness of these tests happens to be the structural engineer who trained me. His name is Nels Rosalyn. He's a structural engineer who specializes in historic buildings. For example, he retrofitted the San Juan Capistrano Mission, the San Miguel Mission, the Bradbury Building in Los Angeles, and the Bradbury Home in Los Angeles. Now, these are really priceless buildings that only a real top-notch earthquake hazard mitigation engineer could address. He also was a co-author of the Seismic Retrofit Guidelines for existing buildings, which is where I found him because his name was at the front of that. And, being I was really trying to learn this stuff as best I could. So I found his name and I contacted him. And we developed a close friendship over this time. Nels also helped write this report on retrofitting steep hillside homes, and he also taught us how to retrofit these homes using steel braces rather than doing any foundation work. And so he is the one who actually looked at these tests. And I'd like to point out that these existing building materials that were tested, what happened is there was, I talked about the 1971 earthquake in San Fernando, and that team went out and looked at all these existing buildings, and they were actually all brick buildings. And so they went and looked at all these brick buildings, and they also had walls, they had wood floors, they had all this stuff. So they took that stuff apart, and they saw, how they were built. And remarkably, they discovered that all over the country, they were pretty much all built the same. So when they did these tests, they would build a wall that was identical to the ones that they saw in these brick buildings, and then they would subject it to these tests. Now, he told me the way these tests work actually just a couple of hours ago, and what he said was that they would subject them to a dynamic load identical to what an earthquake would create. So the testing equipment at this aerospace company was just top-notch and unbelievable. So they tested walls, they tested floors, they tested absolutely everything. And he said that the tested value that's listed in the table, that was actually the point at which the specimen was failing to the point that if you continued, in probably 10 or 15 seconds, it would become obliterated. So that is the tested value that he was looking at. So anyway, he is, he's the first person to counter this whole thing, and I really felt responsible to get this information out to people. This is actually history. I remember looking at that table a long time ago, man, where did they come up with these numbers? And then I found out through Nels Rosalyn, and like I said, he is the last living witness of how these tests were performed. The research team was led by a structural engineer who's well known in the engineering community. And Nels Rosalyn also worked for him, except Nels got involved with this project towards the end of it. So he said he wasn't all that much involved, though he was fully aware of it. So the research that was done by the engineers on the brick buildings, that actually ended up being chapter A1 of the seismic retrofit guidelines for existing buildings, which deals with masonry buildings. And actually that's where this table is found. It's not found in the wood section, which you would think it would be because everything there is about wood, but this is also found in masonry buildings. So this code, or this table, is extremely important for home retrofits just as it is for masonry buildings. Notice that this table lists the strength values of existing materials, and a strength value is the maximum amount of force a material can resist until it completely fails. So for example, let's say we have 1 linear foot of stucco, and that is plaster on metal lath, and we apply 600 pounds of lateral force to it, and then it fails. I mean, it completely fails. It can't resist anything anymore. Now imagine it as like a weightlifter. A weightlifter is lifting up 600 pounds. Once he gets that 600 pounds, he can't do a bit more. He has to drop it. He can hold it there for a second, and that's it. And it's just like that with earthquakes. It can resist 600 pounds, and then once it gets to that point, it just can't hold it anymore. So that 600 pounds is, you're stretching the material to its maximum. It's not, it doesn't have any more strength than that. Now over time, that table was changed. And when I was first starting this business, I was using the 1997 Uniform Code for Building Conservation, and it had this table here, which is the allowable value. And that lists stucco at 200 pounds per linear foot. So imagine it like this. The same weightlifter, if he has to pick up 200 pounds, he can hold it for a long, long time. Eventually he's going to have to drop it because he can't hold it forever, but he can hold it for quite a while. So imagine it just like this with an earthquake. So in this table, the building code is telling the designer that whenever he's looking at a wall, to evaluate, he can just assume it can resist 200 pounds per linear foot and no more than that, because it'll just sustain too much damage. This reduction from a tested value to an allowable value is also called a safety factor. And what that means is the building department will say, you know what, maybe the engineer didn't design it right, maybe the building materials were defective, maybe the building inspector didn't notice something, maybe the contractor, screwed up. There's all these different things that could have happened. And then it'll say, well, you know what, if we give it this particular value, we can pretty much count on that, because even if somebody totally screwed it up, it still should be able to resist that much force. So just to be safe, you have that lower value. So let's see how we apply the information in this table to an actual house. So here's a sample 1,000 square foot house. It's 25 by 40, and it's got its plaster on the inside, it's stucco on the outside. It's what's considered a heavy house at 50 pounds per square foot. And we determined that it must resist 5,000 pounds on each side. So over on this side here, where it's 40 feet long, there is plaster on the inside and there is stucco on the outside. So here we have 40 times 200. Remember, we're using the allowable value, and that gives us 8,000 pounds of resistance on the outside, 8,000 pounds of resistance on the inside, because plaster and stucco have the same value. So we end up with 16,000 pounds of resistance as is. And if we only need 5,000 pounds, there's really no point in doing any work here. There's absolutely no point at all. Now, some people might be concerned, well, how well is the floor connected? And here we go back to Appendix Chapter A3 of the California Existing Building Code, and what it tells us there is that connection, you just don't need to worry about it. It does not need to be verified. So there's no extra metal, no connect that needs to be made there. And it's our experience that the mud sill, you'll find a nice big, a 20 penny nail about every 2 feet, 2 to 3 feet along the whole wall. And that's, probably sufficient. But if you want to go ahead and augment it with some URFPs on the outside, you could go ahead and do that. Anyway, you'll have a really strong wall without doing anything, and you don't compromise the the fire safety. You don't they have to paint it. It's really expensive to do seismic retrofit work, and this will save a lot of money by using this table which we've just researched. Now there's one part of this table we don't use very much, and that's the part that has to do with horizontal diaphragms. A horizontal diaphragm is either a floor or a roof, and because those things don't fail in earthquakes, we don't look at that part of the code, except in one case. Now there's a part that says floors with straight tongue and groove sheathing, 100 pounds a foot in seismic shear, and let me explain what that is. A horizontal diaphragm with straight sheathing would be one like this, and it has boards that, just run straight across. So they're just boards that, run like this, and they don't have any angle or anything. Now, if you take that and you move it up like this is basically the same thing as a wall. So that would be a wall with straight sheathing. So this is the same as this house right here. So you see how there's boards that run like this? Those are actually tongue and groove boards. So that means they sort of interlock together. And then you can see the siding comes this way and the siding comes this way in a horizontal fashion. Same thing over here. It's in a horizontal fashion. And you can barely see this house over here, exact same, boards in a horizontal fashion. And these boards are actually the weakest sort of siding you can possibly have. So that's 100 pounds per linear foot. Now compare that to stucco, which is 200 pounds per linear foot. So stucco is actually twice as strong as is than wood. Stucco does have problems though. Stucco is a very brittle building material, and what happens in an earthquake, it just snaps, and once it snaps, it loses all ability to resist the lateral forces of an earthquake. So as you can see right here, the floor slid on top of the foundation. Now notice this is not a cripple wall. This is a solid foundation, and when it slid like this, that's where all the damage happened. Now, this could have been retrofitted if it had shear transfer ties, especially. You would not have seen this kind of damage. You want to read about shear transfer ties and how they're important for houses built like this, please go ahead and look at the card above. This is the end of the video on archaic building materials. As you can see, it's extremely important. We can't figure out what a house needs until we know exactly how strong it is, as it is right now. So anyway, I hope if you're an engineer, contractor, a homeowner, you're looking at a house to see how earthquake resistant it is, I really hope that you can do a better job in the future.